So, welcome to our series of lectures on understanding Higgs mechanism. We have discussed, from standard model, we know that we have three types of particles according to the standard model. We have three types of particles: particles of spin, half particles, those are called fermion particles. Fermion particles having spin half. Boson particles, those follow Bose-Einstein statistics are called bosons. Those follows Fermi-Dirac statistics are called fermions. So boson particles have spins 1, and the last is Higgs particle with spin 0. So we will discuss the Lagrangian of each one of them: fermion Lagrangian, then boson Lagrangian, and Higgs Lagrangian. Also, in the last class, we discussed the electromagnetic field, and we have electromagnetic field tensor. Field tensor. Of course, this is a boson. This comes into the boson category. The electromagnetic field tensor is, we have worked out that this is denoted as F nu nu, and where F nu nu is delta A nu delta A mu delta X. Mu and nu are the indices which has three components: 0, 1, 2, 3. 0 corresponds to time component, 1, 2, 3 corresponds to space component, X, Y, and Z components. So now today we are going to discuss the Lagrangian for fermion particles. The we know that the Dirac equation for spin half particles or for fermions is Dirac equation for spin half particles this was energy on IH cross psi by del T. This is equal to C alpha times P, where alpha and beta are introduced by Dirac, plus m beta C square. This is operating on psi. Where psi is the field function for spin half particles. Now, this can be written as IH cross. P, IH cross, then plus m beta C square. Because you know that the momentum can be written operator form in this way. So this capital S also like this, H cross psi by C dt minus alpha dot plus m beta C. Take the right hand side to left hand side will be you can take H cross here, let it be. Now multiply by beta. Oh, so this will be H cross now we write beta alpha as let beta alpha as gamma and beta is gamma 0 and beta square, where alpha and beta are 4 by 4 matrices here. So if you write these values here, this becomes this is beta square is 1, beta alpha is gamma I, where I runs from 1, 2, 3, x, y, z components. So this is the time component and this is the space component. So these two can be combined, time component and space component, and can be written in a I cross gamma mu delta by delta x mu minus NC so this is our Dirac's equation for spin half particles, where alpha is related to Pauli's spin matrices and beta is 4 by 4 matrices. I will write like this. So alpha, so alpha is Pauli spin matrices. These are Pauli spin matrices. Sigma 1 is 0, 1, 1, 0. Sigma 1, sigma 2, which is x comp, sigma 0 minus pi, pi 0, and sigma 3 is 1, minus 1. So all these are Pauli spin matrices. So this is actually a 4 by 4 matrix alpha. If you write, this will be 0, 0, 0, 0, sigma I. If it is alpha x, so the x component will be 0, 1, 1, 0, and 0, 1, 1, 0, 0, 0. Similarly, for x, alpha y you will get, you will use this one, sigma 2, and for z component. And beta is also a matrix. This is 1, 0, 0, 0, 0, 1, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. So all these means this is actually 4 differential equations, and since this psi has 4 components, psi 1, psi 2, psi 3, psi 4. These alphas and betas, alphas are related to spin, so it's for every component of psi values, we have particular value of spin is included into. So this includes the spin part. It means the Dirac equation has already spin is incorporated into it. So this is all about Dirac equation. Now we want to find the Lagrange for the Dirac part. Spin half particles, Lagrange for spin half particles. So n is to obtain Lagranges for spin half particles. Lagrange density for spin half particles. This is I cross C minus LC square. This is the kinetic energy part. This is the same gamma and this is actually del mu means del. This is the same here, and this this picks up the particular gamma values for different mu, because this has 4 equations, and so this is the kinetic energy part. The variation of the field psi with respect to the space and time is given here, and this gives you the particular corresponding to whatever mu you have taken, that will pick up the values from here, and this is the conjugate of this, so this becomes a mod. So this gives you the kinetic energy, and this is the potential energy. This is you the phi square. So it's just like we have discussed that potential energy is proportional to the field mod of the field square. So this is the potential energy part, and this is the kinetic energy part. This is the potential energy part for the spin half particles. This is the Lagrange. And if you apply the Lagrange equation of motion, you will get again the Dirac equation. So I am not going to do that because that's not required here. Now. So this is our Lagrange for spin half particles. Suppose this is function psi, field function psi. There is a a change in phase is produced in it. Suppose this is multiplied by some constant phase factor e to power I theta, where theta is constant. So the phase of the field varies. Similarly, this will vary e to power minus I theta psi. So if you substitute this value here, instead of this, suppose we have changed this new Lagrangian, where the phase factor psi undergoes a transformation by a phase factor of this much. So if you do that, you will get I cross C. This is e or minus I theta, where theta, of course, where theta is here constant. Theta is like constant phase factor. So theta here e power I theta psi minus m c square. If you substitute the values of these this phase factor will cancel out. If you again this gives you, this is the changed Lagrangian, changed by phase factor. So it's, this will again give you the same value. Oh, sorry, it's, I missed this one. It's you here. This is again the same thing. Which means if you change the field value by constant phase factor, there will be no change. The Lagrangian remains invariant by the transformation by constant phase factor. Now suppose this phase factor is not constant but varies with say some values of, depends upon x, the x is space time. Then this, now suppose that this type of transformation where theta remains is constant by the transformation of phase factor is called global gauge transformation, and globally it's the same. Now if you want to change, suppose theta varies with space time. Yeah. I now apply this transformation to our Lagrangian. Our Lagrangian was H cross C. Minus MC square. Now instead of taking the value of psi, I am taking the value of this value of psi. So the new Lagrangian will be I cross C. Instead of this will be I theta. It depends upon x also, and gamma mu, and this. This factor will remain same because this will cancel out here. I theta x minus I theta x. So this side will remain same. Now here, this will value will change. Differentiate this one, you will get I so this will be differentiated this one. Del by del x, so x depends upon x space time plus now this part is constant and this will be now this m c square so obviously this Lagrangian is not equal to this Lagrangian because we have a factor, this factor, extra factor. So the extra factor, so it is I cross C. This is psi star gamma mu. Okay. This and this e power I theta minus theta minus LC square. And this factor, which is I square minus 1 h cross C this is an extra term. This one will be extra term. Multiply this one. I square is equal to minus 1 hc e power theta cos. Oh, sorry, here I have this. I theta. This cancels out. This remains. So this is an extra term. The Lagrangian is different. Now we will do some trick to remove this extra term. We introduce a new field. Let us introduce a new field which varies. Suppose we have taken this. Now let us consider a new field. Consider a new field A, where A transforms as A mu plus delta mu of some factor lambda, where lambda is minus hc by 2 times theta. This is just to absorb this part, so that Lagrangian becomes invariant. Now I have introduced a new field. This is a trick to make the Lagrangian invariant. So the new Lagrangian will be the new Lagrangian I cross C is our old Lagrangian. We add something which we take the values of this field also. So, and this, the added quantity is Q this is the added field. Here we have added A mu, and this is the interaction part of the fermion field with this new field A mu. This is the interaction part. Then Q is the coupling constant, the constant with which these two interaction couples. So the Q gives you the magnitude of the coupling constant. Now now again use the transformed Lagrangian. So this part, the transformed part is here. So the transformed part is already written here. I will not write it again. This part of transformation plus Q size Q E itself. Oh, sorry, it's minus here. It's minus here. Yes. So instead of this is e to the power minus I theta x. The transformed part this, and the transformed part of this is so it is A mu it must be plus. It must be plus. Let's see. Oh no, sorry. It's again correct. Correct. It's already it's minus. It was minus. So it is Q, there's a transformed part of this is e to the power minus I theta. And this A mu's transformed part is, so it's A mu or d lambda means minus of hc by q, hc by q theta. And this again A or I theta. If you open the bracket, you will see that this part cancels out. It will be an okay, I will write it like IH cross C. Okay, minus mc square. Okay, it's better I write right here. psi h cross c minus mc square minus hc now this minus q e to the power minus I theta e to the power I plus I theta. That's now this one minus minus plus q cancels out and this e to the power minus I theta is finished. So it will be plus hc psi bar gamma mu delta mu theta. So in this equation we find that this and this cancels out and you are again left with the same Lagrangian. So just adding a new field to the Dirac-Lagrangian we have made this invariant, gauge invariant. So it means this L prime is in L only by adding a new field to the Lagrangian, and the added part is this is the added part is actually the interaction of the psi field, fermion field, with A field, and A field is the electromagnetic field. And so this is the interaction of the fermion field with the electromagnetic field makes this Lagrangian invariant. So, okay.